Hello everyone. The title of today's lecture is Functions and their Graphs. So in the today's lecture, we'll try to understand what is the meaning of these graphs by recalling some prior information or prior knowledge which we have already covered in terms of the functions. So I'm going to give a quick recap of what was domain range, and we'll try to build some motivation required again for these graphs, from the information or from these functions. So there are two approaches which we're going to understand what is a function as a machine and as an arrow diagram. After covering these observations, we'll move forward with the graphs of the functions, and finally what is this vertical line test. The third point is a very important tool which we're going to use to test whether the given graph which we're going to sketch is a function or not. So let's start the today's lecture. So now if you see here, we'll try to understand what is a function as a machine. Now if you see this pictorial representation, this small f, which was a symbol which we use while defining a function, this small f is a tool which will help us to transform some input values to an output values. And what this tool is basically, it is a function which is acting as a machine. In machine, if we give some input, then let's take an example. Suppose we want to construct some product. Then for that product, in the very starting phase, there is some raw material which is used and which is given to the machine, and after some process the machine gives a product at the final stage. So in between, whatever the machine is processing, it's a kind of a rule which is assigning those inputs some certain output, and in that case the input is a raw material, the output is the resulting product which you want to use. So in mathematics, the concept of functions can similarly define in terms of this machine. So the input values are the values of the domain. The values, these small x, are our input, which we are giving to this small f, which we are calling as a function, and the output values which we are getting are our product in our case. And in fact, these values are nothing but the images corresponding to the values of the domain. If you recall, what was a function? A function was a rule which assigns a unique element to every single element of the domain. It assigns a unique element in the codomain. Fine. So this small fx, where it belongs? It belongs to codomain. And this x was coming from our domain. So I can say now, this domain was the collection of all the inputs which we have, all the input values. The range was collection of all the output values, and the codomain, if we recall, our small f, this map, this function we are calling, was defined from some set A to the set B. So the domain of f was a set of all input values. So in our case, it is this set A. The codomain of this rule is the set B, and finally the range. This is a very important concept now which we're going to use throughout the course. So try to understand this. Range is collection of all the images. So your images looks like this, an expression of the form fx. These are your images, such that these images you are getting corresponding to the elements from the domain. So x belongs to the domain of f. This is very important for us. Let's try to understand it again. What is the range? Range is nothing but the collection of images. You take all the images and collect it in a set, make a good collection. So the collection of those fx corresponding to the values of x which you input are your range. And obviously these all the values which you are getting belongs to this codomain. So this set is a subset of the set B. This is an observation. Fine. Let's move ahead. So we understood how a function can be represented in terms of a machine. Now we're going to understand how a function can also be represented in terms of an arrow diagram. So if you recall, we have already even covered how to represent this in terms of the arrow diagram, but today I'll try to make it a more easier for you. Suppose your set is of this form. Suppose this is your some set, and here is again a set. It is not hard and fast to always make set in those vertical ellipses notation. You can just make it like this also. So if this is your set of input values. Suppose here I am taking some of the values. This is your x, this is your y, this is your suppose z. Corresponding, suppose here it lies fx, here is your f of y, and here is your f of z. I am just picking some of the particular values from the this set is basically what this set represents. This is our domain. This set is our domain. This is a codomain, basically set containing the images. What this set is, it is containing all the images, and it is precisely the codomain. So if you see now, this element of the domain is assigned to this element of the codomain using that rule, and what is that rule is using this small f. Again, this element y, there is a element f of y present inside the codomain. Similarly, for this z, there is a fz. So you can see, corresponding to every element in the domain, there is a unique assignment in the codomain. Fine. So this was the concept of how a function can be described in terms of an arrow diagram. So if you see now, what I have just mentioned in this bracket, that we will now try to identify some functions, and basically we'll try to identify the domain and range of some functions. We have learned the definition. Now let's take practical examples. So let's rub this now. Now, let's take an example. Suppose, very first example which I am trying to take is my fx is this square root of x. Now, how I define my f to be the square root of x, corresponding to each x I am getting this quantity as an output value. Now, I ask you to just pause the video and just try to think once, what are the possible values which you can give into this expression? What are the set of possible values? Just make a pause and try to think it once. Let's try to understand what are those values. If you see in the real number system, where we are trying to understand all these concept of functions, we are assuming the largest set which is known to us is this set, the set of real numbers. So in that particular set, the possible choices of x which I have, which I give them as an input, is all those values, either they are positive or certainly 0. I cannot assign any negative value to this square root of x because this is not defined in this system. So this x can only take either value positive or equals to 0. So if I combine these two values, I have an option to take x greater than 0, and such values are called non-negative. So these are the possible values for which this function is defined. So I can give all these as an input value. So your domain is now, what is your domain? I ask again you to pause the video and try to find it yourself. The domain is very simple now. You collect all those x which are greater than 0, and of course they are apart from this. So basically you are talking, you can choose the domain to be this closed interval. You can include 0 here, 0 to infinity. Fine. Now we'll try to identify its range. What are the possible output values which we can get? We are now interested in answering this question on the right hand side. Basically, what are the possible set of values which this function can give us in the form of outputs? So we have now understood what is its domain, basically the set of all non-negative real numbers greater than or equal to 0. So whatever quantity you are going to give, either 0, if you choose your x to be 0 itself, then in this case your f of 0 is the square root of 0, which is of course 0. If you choose any value x to be positive, suppose say I choose for convenience, just for sake of calculation, if I choose 2, then my f of 2 is square root of 2, and which is again a positive number. You will find indeed that this function gives output all the non-negative values again. So when I will be discussing the graph, you will going to easily understand how the range of this function is basically again the same this interval 0 to infinity. Fine. So I'll be answering in this video itself when we'll be discussing how the graph is defined. So let's now try to rub this and move forward into the second outline and try to understand what is the graph and why we need these graphs. Whenever we are studying functions, graphs play an indispensable role. Thus, graphs are very important while studying functions, because from the graph you can interpret certain characteristic or behavior of a function, which will help you to comment somehow later on when you will going to investigate something about the function. So the graph of a function can be defined as a collection of ordered pairs. What it can be defined? Let me now rub this. As a collection of ordered pairs. And what are those ordered pairs? Input values and the output values you collect. Basically, in the set theoretic notation, the graph is collection of those x, fx, such that this x belongs to the domain of f. Right? So this is how your graph is defined. In our case, we know this x in this particular case, if you recall, the domain of f was this interval 0 to infinity, that is your x belongs to this interval. Now if you try to plot it, let's make a good graph of it. Fine, this is our xy plane, Cartesian plane basically. Here is the origin. This is the positive x-axis. This is the negative x-axis. Indeed, we don't require this for time being. And this is a positive y-axis. This is negative y-axis. These are all the possible values of x which you can give as an input. These are all the possible values of x which we can give as an input, because we have already understood its domain is this. Now we'll try to identify some of these inputs and corresponding some of the outputs, and finally we're going to sketch this graph. If I now extend this is a positive part of the x-axis. Corresponding to the point 0, I have an output 0. So this is how my this is the point 0, 0 I have 0, 0. Corresponding to this x equals to 0, f of 0 is square root of 0, which is indeed 0. This is the point. If now I choose my x to be, suppose say 1. Let's take some good values. 4. You can choose more values. Corresponding to x equals to 1, your output is square root of 1, which is indeed nothing but 1, 1 itself, because square root of 1 is 1. So this point, if you plot here, it will be something like this. Corresponding to x equals to 4, you can now easily calculate. Substitute x equals to 4, the answer is 2. Square root of 4 is 2. So this point lies somewhere here. Double the height. Fine. Now if I try to join these 3 points, this smooth curve, this is how the graph of this function looks like. It is going in this particular direction. As you will going to increase the values of x, you will see the values of y also increasing. The values of y which you are getting, basically those fx lie on the y-axis. So if you collect here, you see the y values are now growing on this, because the graph is increasing in some sense, if you see. So it contains all the y values. It contains all the y values. So that's why a range of this function is 0 to infinity. Fine. I hope you got it right. Now let's move ahead and take some more examples to identify again what are the domain and corresponding range of these functions. Now let's try to understand this example. Fx equals to 1 by x. Again, we'll try to identify what its domain is, what its range is, using the same analogy which we have used in the previous example. So if you see, now if I ask you this quantity 1 by x, where is x are real numbers. So now I ask you to pause the video and think it again. What are the values of x for this function is defined? What are the possible values of x? If you see now, what is the problem here? For which input there is some problem. We know from prior knowledge that we cannot divide, it's not possible for us to divide any fraction by 0. In the denominator, we will not able to take 0 value. Why? Because if we take any value 0, certainly this quantity will tend towards infinity, which is not a real number. So if I now plot my again that xy plane, so in this plane there is a gap now. This 0 I cannot take, I'm not able, it's not possible for me. So directly I can remove my 0 from the domain. Whatever the set I'll be getting, 0 will not be present. Now if you see, except 0, for all the other possible values, this function is defined. This function is defined for any other value. So definitely, now from here we can say in general, the domain, whenever we are defining some function, the domain can be understood as the largest possible set of values for which the function is defined. Try to understand again, the domain can be understood as the largest possible set of input values for which it is defined. So in our case, we can say it is defined for all values except 0. So all values are on this real line, real number line, I am not able to take 0. So this is my domain. Fine. So you got a clarity that this function is defined for every value of x except at x equals to 0. So all those x which I am able to take are real numbers. So from that I am just trying to eliminate, or I am not taking 0. So this is that set difference. From the set of real numbers I am excluding 0. So basically the domain is the collection of all the non-zero real numbers in our case. So if now I plot its graph again, if you see some of the points, suppose say I choose x to be 1, the output is also the same. You can just substitute easily f of 1 by 1, which is read 1. So the corresponding to this input 1, the output is also 1. So this is your ordered pair, 1 comma 1. So here your point lies here. This is your point. Now choose a point less than 1. Suppose I choose a point half. We have understood its domain is. So let's use a space. So the domain is of f set of all input values except 0. So I can like rewrite it as the union of two intervals. See, from here to here I can write it like minus infinity to 0 open interval, union 0 to infinity. From here to here 0 is not included anywhere. So this is a way of representing the domain. Now we are interested in answering this. What is its range? I ask you to choose a value less than 1. Suppose I choose x equals to half. Then what is the output value corresponding to x equals to half? My f of half is 1 by half, which is 2. So the ordered pair which I get, half comma 2. The value is twice. It is certainly here. If you choose 1 by 3, it is somewhere 1 by 4, not 1 by 3. then the output is 4. If I now extend this, the output is somewhere here. Now choose a very large value. Suppose I ask you to choose a value 1000. Then f of 1000 is 1 by 1000, which is indeed 0.001. You observe something, make an observation, a good observation. If you can see all the values, if you choose less than 1, of course greater than 0, this is where 0 lies here, the origin. All the values which are positive strictly less than 1, then the output values are very large. All the values which are large enough, the output values are very small. Suppose this is my 1000 here, and this is a very small value. This is an approximation. So if now I try to sketch its graph, this graph will be something like this. Similarly, if you will try to plot the negative values, what will happen? Only the sign of the y values will change because we are taking negative values. So the graph will reflect around this x-axis and will look something like this. So you see, the graph says the y values. What are the y values it is taking? Try to make an observation. I ask you to pause the video and try to think it yourself. From here, if you see, it is taking all the positive values as its range. From here, it is taking all the negative values because the y values are varying. So only the value it's not taking is the 0. So again, the range is also same in this case. What is the range? I hope you got a clarity. We have covered now two starting points of the outline. What are the function in their domain, codomain, function as a machine, as an arrow diagram. And also we have covered the second outline. We have defined how the graphs of functions defined, and we have identified the domain and range. Now we move ahead with this outline, the vertical line test, and it's very useful for determining whether the graph you sketch, whether the curve you sketch in the Cartesian plane, xy plane, is a function or not. What it means basically, why this concept is defined. Every curve which you sketch need not be a function in the xy plane. And how with the help of this test we can identify whether any given curve is a function or not. From the definition itself, from the definition of function, it says for corresponding to one input value there will be only one output value. So, but there are certain curves on which this condition is violated. Let's try to see this example. If now I sketch, suppose, a circle, right? But I'm trying to sketch a circle. This is my circle, unit circle of course, 1, minus 1, 0. The heights are also 1. This is unit circle. Now if I draw a vertical line, suppose like this, but I have just sketched a vertical line. There will be some value, suppose say half, x equals to half. This is the vertical line. So now if you see, corresponding to this half here, this is your input value of the domain. There are two possible output values. One is here, another is here. But as I have already said, in a function corresponding to one input value, you can have only one output value. So this curve which we have just defined is not a function, because corresponding to half you are getting two output values. The equation of this curve will be x square plus y square equals to 1. So if you now try to find, the y will be 1 minus x square root, and it is plus minus y. There are two values for y. Either it will be this or it will be this. This y is certainly your f of x. So this how you can rewrite the curve. Wait. Now right now I'm not. Sorry. Yeah. Right now I'm not going to write this, because what I want you to observe first, that corresponding to this half, from this vertical line we find that this curve is not a function, because we are getting two values. For half we are getting this value is 1 minus 1 by 4, so 3 by 4, so square root of 3 by 4, that is square root of 3, this values, and this is minus root 3 by 2. You can calculate from these equations, just substitute as x equals to half. Basically this ordered pair you're getting half, but which is not possible. So this is not a function. This curve which you have just sketched in the previous example, draw any vertical line on its domain. You see, corresponding to this input, there is only just one output here. You should draw any vertical line on its domain. You will find corresponding to every input value, there is just one output value, like this here on the curve. So such example is of a function. This is not a function, but you can now redefine it, or you can now, you see, if I just see this one part of this curve at a time, if I now take only this upper semicircle or this lower semicircle, then we can define them as functions, taking only in account one at a time. So you got a clarity on what is this vertical line test, and this is how it is very useful for determining whether a given curve is a function or not. So we have understood our outline today. In the coming lecture, we will be discussing examples, some good examples of functions, which will be very helpful. So do like the video and do subscribe our channel. Thank you for watching. Thank you so much.